A fundamental transformation is occurring in the semiconductor industry that threatens to reshape the entire computing landscape. Major technology corporations are quietly abandoning decades-old processor architectures in favor of an open-source alternative called RISC-V, and the implications extend far beyond simple cost savings. RISC-V represents a fundamentally different approach to processor design. Unlike the proprietary x86 architecture dominated by Intel and AMD, or the ARM architecture that requires expensive licensing agreements, RISC-V is an open instruction set architecture. This means the basic blueprint for designing processors is freely available to anyone, without royalties, without restrictions, and without corporate gatekeepers controlling its evolution. The architecture itself embodies the principles of reduced instruction set computing, featuring a clean modular design with a base set of just 47 instructions. This simplicity stands in stark contrast to the bloated complexity that has accumulated in x86 processors over decades of backward compatibility requirements. The elegance of RISC-V allows engineers to understand the entire instruction set in a matter of hours rather than months. The financial incentives driving this transition are substantial but often misunderstood. While RISC-V itself is free to use, the real savings emerge from the elimination of per-chip royalties that can amount to billions of dollars annually for high-volume manufacturers. ARM, for instance, typically charges between 1% and 2% of the chip's selling price, a fee that compounds dramatically when producing hundreds of millions of units. Beyond monetary considerations, RISC-V offers unprecedented customization capabilities. Companies can extend the base instruction set with proprietary additions tailored to specific workloads, whether that involves artificial intelligence acceleration, cryptographic operations, or specialized signal processing. This flexibility is impossible with lockdown architectures where every modification requires negotiation with the IP holder. The geopolitical dimension of this shift cannot be overstated. In an era of increasing technological nationalism and export controls, relying on architectures controlled by companies in specific jurisdictions creates strategic vulnerabilities. RISC-V, being open and internationally governed, provides a neutral foundation that transcends national boundaries and political tensions. Chinese technology firms have embraced RISC-V with particular enthusiasm, viewing it as a pathway to semiconductor independence. Companies like Alibaba have developed high-performance RISC-V processors capable of competing with established architectures, while the Chinese government has made RISC-V development a strategic priority in its technology roadmaps. Western tech giants are equally committed to the transition. Google has integrated RISC-V support into Android and is developing RISC-V cores for various applications. Meta has invested heavily in RISC-V research for data center optimization. Qualcomm, despite its deep ARM relationships, is exploring RISC-V for specific use cases where customization provides competitive advantages. The technical maturity of the RISC-V ecosystem has reached a critical threshold. Sophisticated compiler toolchains, operating system support, and development environments now rival those of established architectures. The RISC-V International Organization coordinates standardization efforts, ensuring compatibility while allowing innovation to flourish. Performance benchmarks increasingly demonstrate that RISC-V implementations can match or exceed ARM and x86 processors in specific domains. While general-purpose computing still favors mature architectures with decades of optimization, specialized applications like machine learning inference, embedded systems, and edge computing show RISC-V pulling ahead in both performance and power efficiency. The software ecosystem presents both the greatest challenge and the most significant opportunity. Decades of optimization for x86 and ARM have created enormous software libraries, but this legacy also represents technical debt. RISC-V offers a clean slate, allowing developers to build modern software stacks without the constraints of backward compatibility. Security considerations further motivate the transition. Open architectures enable independent verification of processor designs, making it possible to audit for backdoors or vulnerabilities that might exist in proprietary systems. This transparency is increasingly valuable as processors become targets for sophisticated attacks. The economic disruption extends throughout the semiconductor supply chain. Traditional licensing models that concentrated wealth among a few IP holders are giving way to a more distributed ecosystem, where value accrues to those who can innovate on top of the open foundation rather than those who control access to it. Manufacturing considerations also play a role. RISC-V designs can be optimized for specific process nodes and manufacturing technologies without requiring permission or paying additional fees. This flexibility accelerates innovation cycles and reduces time to market for new products. The transition is not without obstacles. Application compatibility, developer familiarity, and ecosystem inertia all favor established architectures. However, these barriers diminish as major software platforms add RISC-V support and as a new generation of engineers trained on open architectures enters the workforce. The momentum behind RISC-V reflects a broader shift in how technology infrastructure is developed and controlled. Open standards and collaborative development models are displacing proprietary systems across multiple domains, from operating systems to artificial intelligence frameworks. RISC-V represents this philosophy applied to the most fundamental layer of computing. The semiconductor industry stands at an inflection point where the advantages of openness, customization, and geopolitical neutrality outweigh the comfort of established architectures. Tech giants are not simply switching to RISC-V for cost savings or technical benefits alone, but because the open architecture aligns with a future where control over computing infrastructure is too important to be left in the hands of a few corporations. The secret reason is that there is no single reason, but rather a convergence of technical, economic, and strategic factors that make RISC-V not just an alternative, but an inevitability.